In this lesson, we're going to discuss scientific notation, which is a method that scientists use to represent numbers that are very large or very small in a more convenient and compact manner. Scientific notation takes advantage of the rules of exponents. An exponent is a small number that's written as a superscript to a base number. So for example, 2 is our base here, 1 is the exponent. We would say this is 2 to the 1 power. What that exponent is doing is it's telling us how many times to multiply the base by itself. So if we have 2 to the 1 power, that's just a 2. 2 squared, or 2 to the 2 power, is 2 times itself twice. 2 times 2 is 4. 3 to the 2 power is 3 times 3, that's 9. 2 to the 6 power is 2 times itself 6 times, for a total of 24. And then a special case, 2 to the 0 power is 1. In fact, anything to the 0 power, any arbitrary number to the 0 power, is 1. Another rule of exponents is a negative exponent. Our standard exponents look at how many times the number is multiplied. If you have a negative exponent, it's telling you how many times to divide by the base. So 2 to the negative 1 power, the negative power means that we're dividing by 2 to the 1 power, and 2 to the 1 is 2. 2 to the negative 2 power means that, again, the negative means that we're dividing by it, and we're dividing by 2 to the 2, which is 4, and so forth. So how can we take advantage of these rules of exponents when we are representing very large or very small numbers? Well, we use a base 10 system, which means that each column represents a power of 10. This is the ones column, that's 10 to the 0 power. The tens column is 10 to the 1 power. The hundreds column is 10 to the 2 power. And the thousands column is 10 to the 3 power. What that means is that moving the decimal place, the decimal point one place to the left, is equivalent to dividing by 10. So for example, if I take 3,127 divided by 10, I would get 312.7. I've effectively moved the decimal point, which was originally here, and I've moved it one place to the left, which is what we're seeing right there. If I take my 312.7 and divide by 10, it's as if I've moved the decimal point another place to the left. And so what we're going to do is take a very large number that has some significant figures and some placeholders, and we are going to focus only on the significant figures. Those are the only values we actually want to keep. One of the benefits to scientific notation is to allow us to drop all the placeholder numbers. So in this case, I'm going to keep only the first 4 digits. The last 2 are placeholders. The second thing is I want to focus on the most significant digit, the most important digit, the largest digit, right? The largest value is going to have the biggest effect on the overall value of the number. And so what I want to do is move the decimal point until it is just after the first digit. So I want to put my decimal point here. In order to do that, I have to move the decimal place from its original location. In this case, I have to move it 1, 2, 3, 4, 5 places to the left. And what I said was moving the decimal place to the left is the same as dividing by 10. So if I've moved the decimal point 5 places to the left, it means that implicitly I've divided by 10 5 times, or I've divided by 10 to the 5th power. In order to maintain the value of my of this number, if I'm dividing by 10 to the 5th, what I have to do to cancel that out is explicitly multiply by 10 to the 5th. So this part here is part of moving the decimal point. This part here stays to cancel out the change in value. So what I end up with is 1.409. Those are the significant figures from that value, times 10 to the 5th. This is a much more compact way of expressing this number. It keeps only the significant figures. I've dropped the non-significant figures, so there's less writing, there's less chance for me to make a mistake and miscount the number of zeros I've put there. And I have a power of 10 here to give me an order of magnitude to show how big this number is. Take a moment and pause this video and try to convert this number into scientific notation. Again, we look for the significant figures. There's an implicit decimal point here. There's no explicit decimal point written. So we start from the right and move our way left to find the first non-zero digit, and we see that these two are our significant figures. We know that we want to end up putting the decimal place after the biggest number so that we can focus on the most important part. So we're going to end up with a 4.3. These are our significant figures from the number with the decimal point after the largest value. Then we look at how far we would have to move the decimal point. There is an implicit decimal point at the end of this number. To move it where we want it to go, we would have to move 8 places to the left. Moving it 8 places to the left would be the same as dividing by 10 8 times. And so to cancel out that operation, to maintain the value that we're talking about, we would multiply by 10 8 times. This is scientific notation for a large number. Notice that we have positive powers of 10 for these large numbers, representing large values. We can use the same method for very small numbers. If we have a number that is less than 1, if we multiply by 10, we move the decimal point 1 column to the right. So moving the decimal place to the right is the same as multiplying by 10. So we can do basically the same thing we did before, but in the opposite direction. When we have very small numbers that have a lot of zeros here as placeholders to give us very small quantities, we can use scientific notation to eliminate these placeholders and focus on the important points. Again, what we're going to do is to focus on the significant figures of the number. In this case, we have a explicit decimal point written right there. And so we're going to start from the left and move our way right until we find our first non-zero value. And that and everything to the right of it are going to be significant values, significant figures. So in this case, we're going to end up with 8, 4, 8 are the numbers we want to keep. Then we want the decimal point to be just after the first digit so that we're focusing on the most important quantity, the largest quantity. So we want the decimal point to be between the 8 and the 4. We want it to be there. But to get it there, we have to move 4 places to the right. And we just said that moving 4 places to the right is the same as multiplying by 10 4 times. So if this motion here is the equivalent of multiplying by 10 4 times, or multiplying by 10 to the 4, what we need to counteract that is to then divide by 10 to the 4 to cancel it out. But if we're dividing by 10 to the 4, we'll use the other rule of exponents that we saw at the beginning of this lesson. Instead of dividing by 10 to the 4, we will multiply by 10 to the negative 4 power. So here, multiplying by 10 to the negative 4, the negative exponent means that we're dividing by 10 to the 4, which is what we were talking about here. Again, pause this lesson and take a moment to write this number in scientific notation. Here, again, we have a explicit decimal point, so we'll start from the left and move our way to the right until we find the first non-zero digit. That and everything to the right of it are going to be significant. So in this case, we'll have 1, 6, 0. All of those that are to the right of that first non-zero digit are significant. That 0 is there because we must have measured it and gotten 0. If we didn't measure to that level of precision, we would have just omitted the 0 at the end. I've put the decimal point after the 1, after the largest value. And then I look, this is where I want the decimal point to be. This is where it started. So I must have moved it 7 places to the right. I must have effectively multiplied by 10 to the 7 power. So I have to multiply by 10 to the negative 7 power to cancel that out. You can have 10 to any power, to any exponent in scientific notation, but in our base 10 system, we often group special powers of 10. We usually think in terms of thousands, millions, and billions, etc. 1,000 is 10 times 10 times 10, so that's 10 to the 3. 1 million is 10 to the 6. 100th is 1 divided by 100, or 10 to the negative 2. 1,000th would be 10 to the negative 3, etc. And so we have unit prefixes in the metric system that give us special names and special symbols that we can use to replace these common powers of 10 that we will see. And that allows us to group our numbers in expected ways. And also using a unit prefix here rolls off the tongue a little bit more easily than writing out or explaining, saying out the entire power of 10 for scientific notation. So this is a way to further simplify scientific notation, particularly in a presentation when you're trying to describe or say these values, or in a scientific report when you want to keep the numbers compact so that they don't distract your reader. The scientific notation is easier when you're doing calculations, and the unit prefixes are easier when you're trying to express yourself in words. So to use unit prefixes, we start out with a number, any number that we want, and we convert it to scientific notation, just like we saw how to do. So here we have 4,600 joules. These are our significant figures, and I have 4.6 times 10 to the 3 joules. That is correct. This is mathematically a very simple way to express this, but 4.6 times 10 to the 3 joules doesn't exactly roll off the tongue. It's a little bit of a tongue twister. So what we can do instead is say, well, 10 to the 3 has a special symbol and name for it. 10 to the 3 is called kilo, and I can use a lowercase k to represent that 10 to the 3. So I can remove this 10 to the 3 and put a lowercase k there instead. And so I can express this same number as 4.6 kilojoules. And that rolls off the tongue. It's much easier to say. It's much more compact if I'm writing it in a report. This value is still easier to use if you are plugging into your calculator. We can do the same thing with this number. I have 5.30 times 10 to the negative 6 seconds, but 10 to the negative 6 has its own unit prefix. This is micro, and it uses a Greek letter mu. It looks something like an M, but it's different. It is a mu. And so I can replace this 10 to the negative 6 with a mu symbol there, and I can call this 5.30 microseconds. And again, it's a more compact way of saying it or writing it. The power of 10 does not always perfectly align with the special prefixes. These special prefixes go up in groups of 3, so sometimes you'll have a value that doesn't quite work like that. For example, here, if we put this in scientific notation, this would be 7.5 times 10 to the 4 seconds. And so 10 to the 4 is not one of our special powers of 10. What we can do is break this up. 10 to the 4 means 10 times 10 times 10 times 10, 10 multiplied together 4 times. So I can group that as 10 times 10 to the 3 instead. This is still 10 to the 4, because it's 10 times 10 times 10 times 10. Now this 10 to the 3 is kilo. This 10 is by itself, so I'm going to group it back with the 7.5. And 10 times 7.5 is 75. And my K symbol for kilo, seconds. I can also just look directly at the number. I know that I'm moving my decimal to the left, so I'm going to be multiplying by 10. I can move it 3 places to the left to get me to kilo, and I can see that I'd have 75 in that case, 75 kiloseconds. The same thing here if I have a very small number. I have 1.3 times 10 to the negative 4 watts. 10 to the negative 4 is also not one of my powers of 10, so I could break that up and make that times 10 to the negative 1 times 10 to the negative 3. 10 to the negative 3 is milli. And now I have a spare 10 to the negative 1. 10 to the negative 1, remember, means we are dividing by 10. And so 1.3 divided by 10 would be 0.13 milliwatts. I can go the other way with this as well. 10 to the negative 4 is smaller than 10 to the negative 3. It's bigger than 10 to the negative 6. So I could go either way with these values if I wanted to. For example, if I'm moving my decimal place 1, 2, 3, 4 places to get 10 to the negative 4, I could also move it 5, 6 places to get to 10 to the negative 6. That would give me a decimal point here, which would give me 130. And then 6 decimal places would be micro. I would use mu here, 130 microwatts, which still gives me the proper number of significant figures. I could do the same thing up here. I could move my decimal place 6 places here and have it here. Implicitly, there'd be a 0 there. And I could call that 0.075. 10 to the 6 would be megaseconds. So it depends. I usually prefer to use the value that gives me a number bigger than 1. This is bigger than 1, this is less than 1, this is bigger than 1, this is less than 1, because you're either, if you fall between two values, you can go to the higher value or go to the lower value. Sometimes, depending on the industry you're in or what other units you're using, sometimes you always default to one particular value. For example, you always use megajoules or gigajoules or something like that in a power system. A couple special cases here. These unit prefixes are always built on top of the standard units. So we've talked about standard units of meters and seconds. And so we would tack these on top of those standard units. We've seen watts are units for power. We've seen joules are units for energy. We can tack these prefixes on top of those as well. One special case is the kilogram. The kilogram is considered the base unit in the SI system, even though kilo means that a kilogram is already 1,000 grams. And so that's one thing that can be kind of confusing, but keep that in mind. Also, when you are given values using these unit prefixes, it's best to convert them back to their corresponding powers of 10 before you begin calculations. For example, if you are working on a problem where you have a value given to you as an energy that is 10 kilojoules, just go ahead and write that as 10 times 10 to the 3 joules, right? You are converting the kilo back to 10 to the 3. And then when you plug into your calculator, you'll plug into your calculator in full scientific notation so that your calculator can interpret those numbers and give you the proper outcome. Finally, there are many metric prefixes. We go from 10 to the 24 all the way to 10 to the negative 24. Because our units, for example, our unit for meter is about 1 yard long, but meters are supposed to measure everything from the distances between galaxies down to the distances between protons in an atomic nucleus. So we have quite a range. Be aware that these exist, and you can look these up if you need them. But in general, what we will need to know for this class are these ones here and these ones here. These are the ones that you'll use most often, and you should be familiar with those.